Welcome everyone. So today's in last previous class, so brief history, like brief recap I will do. So in previous sessions we have learned about flux law, flux, diffusion flux. Okay, we have learned about the what is diffusion flux and what's its significance, etc. And we have after that we learned about the Fick's law of Fick's law of diffusion. Then we learned about the continuity equation. So how this if the concentration is varying with respect to time as well as the position, then we can say we can use this equation. So but the continuity equation is applicable only for the lab fixed frame of reference. After that we come to know about the two interdiffusion coefficients. Coefficients, that is main interdiffusion coefficients and the cross interdiffusion coefficient. And we understood the what is the importance of these coefficients, like how it will affect to the flux value. After that, so we applied this Fick's law for the multi-component systems, that is on Sanjar's equation. And its derivation. So how the dependent and independent variables are being used, and if we have n number of components, then we can have the n minus 1 square number of diffusion coefficients. For example, if we have ternary system, 3 minus 2, 3 minus 1 whole square. That means 4 interdiffusion coefficients is required. So these are the fundamental concepts that we have covered in the previous sessions. Now, in this session, we are learning about how this concentration profile. So in one of my video lecture, I have drawn the concentration profile like this while explaining the importance of cross interdiffusion coefficients. This is the concentration versus distance. So how this concentration profile varies with diffusivity value. We will see for the both binary as well as the ternary system. That topic is nature of concentration profiles in a binary and multi-component system. Diffusion couple. Okay, so before getting into this concept, I will little small thing I will explain how these concentration profiles will be obtained. What is the procedure? First of all, we'll make a terminal alloy. First of all, Okay, these are the terminologies, and A and B. We will join the terminology. After this, we will heat it and allow for the diffusion annealing for some duration of time, so that they will join with each other by diffusing in atoms. This was explained in the previous sessions. This may be towards this side or this side. It depends upon the nature of the uh, Gibbs energy profile. Afterwards, if we cut along the diffusion coefficient, diffusion joining diffusion joining line, then we will use the EPMA, electron probe micro analyzer, to determine the concentration variation from A to B. Then we can obtain the profile. This is the concentration of A. Towards right side, concentration of A is more, and when we move towards the x direction, this is the x direction. When we move from A to B, the concentration of A goes on decreases, and when we are moved from opposite direction, concentration of B goes on decreases. This is the concentration of B. Correct? Yes. This is a concentration profile. How I explained in brief. There are so many steps involved in this one diffusion couple approach to obtain this concentration profile. From this, we can obtain the diffusivity value, flux value, so many outputs we can obtain, and the information is so many information can be obtained with this diffusion profile. So now we have learned that how this diffusion couple concentration profiles are obtained, right? So now we will understand the nature, how this diffusion profiles, so concentration profile varies with the diffusion coefficients. For binary diffusion couple, so for the binary diffusion couple, okay, we can obtain the profile like this. The concentrations are remains constant at the end, and it will varies like this. Okay, so Ca is 0.7, Cb at the one end is 0.1. Consider, and here it is almost same. Ca plus is 0.7 only. Here it is same. Little bit it's higher. We will consider Cb plus as positive side as 0.2. Okay. So this is diffusion zone that we have obtained. Here x equal to minus 35 and x equal to plus 35. These are the x coordinate values. We can obtain the division coefficient values by with the help of this equation x comma t Ca plus Ca minus Ca plus by 2 1 minus error function. So error function of x divided by 2 into root d tilde into t. This is the solution for the binary division couple to obtain the d value. So what are the nature of this division concentration profile? So there are some features are there. First of all, the profile shows the inverted symmetry. Second point is the same diffusion depth on the both the side. Same diffusion depth on both sides. That means here if you see it's point, it's a 35, here it is 35. We have to consider only the value, not a sign. Same diffusion depth is obtained for the both the components. For the both. That means for the A component and the B component, diffusion depth is same. See here it is. So some of the features it's having point, it's 35. Some of the B is having some other value. There may be chances, but in this profile we have the same diffusion depth for the both the components. No peaks are observed. Observed in the profile. And diffusion depth varies by root dt. These are the 5 silent features or nature of the this division couple. So this we can see that here the diffusivity value for this diffusion couple is 1 into 10 to the power of minus 15 meter square per second. Correct? So when we are increasing the diffusivity value, for example, so I will take a whiteboard so that I can explain very well. when we are increasing the d value from 4 times, that is 1 into 10 power of minus 5 to 15 to 4 into 10 power of minus 15 meter square per second. Then concentration profile will be profile will be like this. Can anyone expect what will happen to the concentration profile? See, here it is there. Okay, this depth is increases to double. We know that x division depth is directly proportional to root dt. Then x1 by x2 equal to root d1 by d2. That means, so 1 by 4, it is 1 by 2. That means x2 is equals to 2 times of x1. We know that x1 is 35. We know that x1 is 35. Then x2 will become 70. That means diffusion depth increased to 2 times if we increase the d value 4 times. Okay, this is the relation that we increases the diffusion depth by 4 times. So one more case in this one itself, if we are having diffusion coefficients are different at the both the ends, so what will happen? So A is having different value and B is having different value of D coefficients, then what will happens to the profile? See, towards this terminal, we are having the diffusion coefficient value as 4 into 10 power of minus 15. Okay, but here we have lesser diffusion coefficient, that is 1.2 into 10 power of minus 15. Then that is meter square per second, and here is also meter square per second. Then we can say the slope of this profiles will changes. It's having shallow slope and it is having steep slope. because of its d value. But diffusion depth will changes towards this side and towards this side. So one significant point we can conclude from this one is diffusion depth. About the diffusion depth are not same on both the sides due to varying interdiffusion coefficients. Interdiffusion coefficients. That means diffusion depth is directly proportional to the diffusion coefficients. That is the d value. But one more is no peaks are observed. So we can say, so I will explain what is this peaks and what is its importance in the upcoming video. Now I will both we have seen the binary diffusion couple concentration profiles, but now we will see the ternary diffusion couple. Couple concentration profiles. Okay, so from the Onsenger's equation, so we can write it J1 tilde equal to minus 311 dou C1 into dou X. This is 1 2 dou C2 into dou X. 2 1 dou C into dou X. 2 2 dou C3 into dou C2 into dou X. So concentration profile can be obtained for this ternary diffusion couple. It's like this. So this is a C3 value. Okay, and this is C2 value. So C3 minus is having 0.45. It is 0.6 C3 plus C2 plus C2 minus is having 0.40. C2 plus is having 0.40. C1 minus is having the value of almost 0.3. It is C2 C1 plus is having 0.1. So there are some silent features are present. First one, the profile shows inverted symmetry. Second one, diffusion depth on the both the sides are same. Same diffusion depth for the two components. Same. For is same. Third one is dependent. Third is dependent component. Fourth is diffusion depth is same for both the components. Okay, I have written that one. And no peaks are observed. In the profile. So we have seen the basic ternary diffusion couple profiles. We will, in the next upcoming video, we will see the profiles consisting of small peaks which is having different slopes, and this will have a significance of diffusion of an atoms. If the peaks are there, so what it noting, what it indicates. We are concentrating on those things in the upcoming video. Thank you.